Go.
Hello, my dear students, and welcome to our last video help session for Chapter 4. I'll qualify that because I'm actually going to break it into two parts, hoping that I can make them smaller and easier to upload. Besides the fact that this one got a little bit long. I'm going to do the first 8 questions, and then I'll do through question 13 in the video immediately below this one on your course shell in the course content page of your course shell in Blackboard. That being said, we're looking at solutions. In the first half, they're going to give you a molarity of a solution. And in the second half of the questions, or from question 9 on, they're going to give you, instead of giving you the molarity and asking you to calculate grams, they're going to give you grams per liter and ask you to calculate the molarity. And just work these types of problems in both directions. So, if I might, I was playing around and doing some things in the lab. I'm reminded of my organic chemistry teacher who always kept a tiny, we had open access at Texas A&M to our chemicals. We could just go up to the front or the stock tables and check them out. But he always kept a tiny bottle of glycerin, which we use for applying to corks and letting the corks slip through the stoppers, the rubber stoppers, or the cork stoppers. I'm not that old. We had rubber stoppers when I took organic chemistry in 1973. But he was always afraid someone would take that glycerin and make nitroglycerin, which is this hard. You mix nitric acid with sulfuric acid. That's a little harder than it sounds. And you just add to it anything with hydroxyl groups, OH groups, glycerin, and make nitroglycerin. Or you can take cellulose. I have some cotton and I put it in there and I made nitrocellulose. So I'm only doing this because I found this and I hate teaching this course online. You need to take it in person so you can see the demos, do the lab, smell the chemicals, feel the heat, and see what I do normally. But this is what happens when you nitrate cellulose. You make flash paper, and it disappears. So, anyway, I'll quit playing around and get to our first problem. This is our last problem set. And in exercise 4.4, for the last part of the chapter, dealing with reactions in solution chemistry, they want you to start thinking about the concentrations of the chemicals that are dissolved in the water. So it says, calculate the number of grams of solute, the thing that's dissolved, in each 1.000, 3 zeros, 4 significant figures, 1.000 liter of solution, the thing that you dissolve the solute in other words, the liquid. And it starts out with sodium bromate, NaBrO3. And they want a 0.2593 molar solution of sodium bromate, or they have one. Always go to the mole, and that molar, big M, means, if we can zoom in over here, moles per liter, which we abbreviate moles per liter that way. MOL for moles, big L for liter. I'm old. I got to use little l when I was growing up learning chemistry. And I'll apologize in advance because I frequently don't always write little m, big L for milliliter. I write little m, little l. I may even write little l for liter. but I'll try to adhere to modern, proper conventions and terminology. Now, sodium bromate has 1 sodium, 1 bromine, and 3 oxygens, NaBrO3. Sodium, if I go to my periodic table, in the atomic mass, average atomic mass, it says 22.990 on my table. Not every table's the same. Your mileage may vary. I have another table here and it says sodium is 22.9898, which I guess if you not abbreviate, but if you only have 3 significant figures would be 990. But this one has different, this is the Flynn Scientific Periodic Table of the Elements, has different values, slightly different values for the elements than the other periodic tables I was using. One in the back of a book and another one I have hanging up here at home in my kitchen. So, bromine is 79.904. What? Well, remember, on the periodic table, it doesn't have any values next to those big red numbers or big numbers. 2 numbers in every periodic table. One is the atomic number. That's the number of protons that identifies that element. And the other one is the average atomic mass. We usually don't add any units to it. If you were working with individual atoms and you had, I don't know, you were in the quantum realm and you could work with a single atom, then you could measure those units in atomic mass units. But what happens when we get to our compounding and our making solutions, those values end up being grams per mole. And to get the molecular mass, molecular weight, molar mass of sodium bromate, all you need to do is to sum the masses of the individual atoms. 1 sodium, 1 bromine, 3 oxygens, 15.999. I think those of you using the Flynn Scientific Table of the Elements, a very common periodic table in many classrooms hanging on the wall as well, it's 15.9994. In the end, I end up with 150.891 grams per mole. Those are the units we want to use because that tells me how much a mole of this weighs. And if it weighs 150.811 grams per mole, and this big M equals little moles per liter, and I have 0.2593 moles per liter, and they gave us at the top of the page that I have 1.00 liters, so I've got 4 significant figures everywhere I go, more on the atomic masses. If I just cancel out my moles, I will end up with number of grams in 1 liter. 39.13 grams in 1 liter. Okay, I did this, with 4 significant figures, because even though I have 1, 2, 3, 4, 5, 6 in my molar mass, I can't go to any greater accuracy than I already have with my concentration, 0.2593 moles per liter, or my volume, 1.000 liters. So 4 sig figs, 39.13 is the solution to question number 1. We're going to go quicker, more quickly. We're going to do a quicker job of covering this in a second, but I want to make a point too. Sodium bromide's 22.9898. Can we call that 23? Bromine is 79.904. Can we call that 80? And oxygen is 15.9994. That's 16 in my book. And if you add up 48 and 80 and 23, you get 151. And when you multiply that 151 instead of 150.811 times 0.2593, I just want to make a point about accuracy and precision. What you end up with is not 39.13, but 39.15 grams. If you want to do this, carbon's 12, nitrogen's 14, oxygen 16, sodium is 23, bromine is 80. That's fine with me, because look at the difference it makes. 39.15 is the answer I got instead of 39.13. And when I use 151 instead of 150.891, and that's a difference of 0.02, 2/100ths. And on a percentage basis, divided by the accepted value, 39.13, times 100, that's 5.1112 times 10 to the minus 4. But times 100, that's 5/100ths of a percent difference. I don't know how accurately you work in your laboratory, but for my purposes, that's generally good enough. That's not good enough if you're working in a really tight, analytical laboratory where you need very precise values. But to demonstrate to me you know how to do this, I'm not going to quibble over changes out in the fourth place. Okay? There's your answer. So the next one says, more quickly now, 1.592 molar potassium nitrate, KNO3. 1.592 molar, big M, is the same as 1.592 moles per liter. I want to know how many grams that is. I can't do anything if I do not know my molar mass. So I want to get rid of these moles and convert this to grams. So I take my potassium nitrate, 1 potassium, 1 nitrogen, 14, 1 potassium, 39, and 3 oxygens, 3 times 16 is almost 48, and I get 101.102 grams per mole. When I do that, my moles cancel, and I'm left with how many grams I need in 1 liter. 1.592 times 101.102. I'm only allowed 1, 2, 3, 4 significant figures. So that is 161.0 because it's 160.954. So the only way to round that is up. 161.0 grams. Next one. It says 1.559 molar acetic acid. I've abbreviated this HAC so I don't have to write everything out. But acetic acid is a 2-carbon organic acid, CH3 on the end, C double bond O, OH. This is the H that pops off to give us the H plus acid. It's a weak acid, so there's an equilibrium between this popping off and going back on. But there's its structure. 2 carbons, 4 hydrogens, and 2 oxygens. And if you add 2 carbons, 2 times 12, 2 oxygens, 2 times 16, and 4 hydrogens, 4 times 1.008, you get a mass of 60.052. The other thing you can do, since this is all at home, instead of adding these masses up, which you need to know how to do, but we've practiced this and we've had a separate assignment on this. Just Google it. Just Google acetic acid and or acetic acid molar mass, and you'll come up with something like this. I did not check Google. Their numbers might be different than mine because different periodic tables, but out to 4 or 5 decimal places, I'm sure they'll be the same. Anyway, if it's 60.052 grams per mole, and this solution has 1.559 moles per liter, my moles will cancel. And in this 1 liter, I will have 93.62 grams. The next one, and the last one on the first page, is potassium iodate. Oops, I did this wrong. I did it for potassium iodide. I didn't read that properly. They want potassium iodate, KiO3. So this is wrong. I would need to add 48 to this from my oxygen. So that's 166. 214. This would actually be 214. Oops. I'm glad I did this. KiO3. This is plus 3 more oxygens, okay? So 214. Let me give you your answer. 214 times 0.943, we're good for 3 decimal places, is 201.8 grams of KiO3 in 1 liter of water. 200 grams in a single liter. That's quite a bit. Okay, I will pull this down and do our last 4 real fast. And that is why you're supposed to check your work, especially on a test, right? Or on the ACT or something like that. The next one said I had 0.1065 barium iodide. 1 barium, because it's group 2. It's element 56 there in group 2. It's always a 2 plus, it's ions, and the iodide is group 7, it's always 1 minus. Iodine is 126.90. Barium is 137.33 grams per mole. I have 2 iodines, so it adds up to 391.13 grams per mole, times my concentration. This big M means moles per liter. My moles will cancel, and I'll end up with 41.66 grams per liter. Here, number 6, sodium sulfate. 1.135, 4 significant figures, molar sodium sulfate in 1.0000 liter. I didn't put that down, but 1, 2, 3, yes, liters, 4 significant figures there. Again, my moles cancel. Do the math. 142 times 1.1, you get 161.2 grams per mole. In this next set of reactions, after I finish these 2, we'll be giving you grams in a liter and asking you to calculate the molarity. So we'll show you quickly how to do that. Now, the next one says 1.428 molar ammonium bromide. Ammonium is a polyatomic ion. These stay together. Bromine is group 7, Br minus. It comes together in a 1-to-1 ratio. We have 1 nitrogen, 4 hydrogens, 1 bromine. If you add it all up, I added up to 97.943. I have 1.428 moles in a liter, and I have 1 liter, so I have 1.428 moles. So it should be about 1.4 times that, and we get 139.9 grams per liter. And finally, it says 0.889 molar sodium acetate. Doesn't tell you what sodium acetate is. They want you to look in a table of the polyatomic ions and see that the acetate anion, which I, as a biochemist, much to the consternation of my pure chemistry friends, frequently abbreviate AC minus. I know that that is C2O2H3 minus. That's the acetate anion, which combines with the sodium cation to form sodium acetate. So I have 1 sodium, 2 oxygens, 2 carbons, 3 hydrogens. It adds up to, these are all, you know, second and third period, first, second, and third period elements. First period, hydrogen, because that's only hydrogen, helium. Carbon and oxygen are second period. This is element number 6, element number 8. So these are smaller elements, and you can see all of these atoms together only add up to 82.034 grams with the accuracy of the periodic table I used. Grams per mole. That's what we can use those atomic masses for. Average atomic masses may be atomic mass units of a single atom of that element, but they're the molar mass of a mole of that element in elemental form. I mean, some are diatomic. If they end with gen or ene, chlorine, fluorine, bromine, iodine, astatine, or gen, oxygen, nitrogen, or hydrogen, their normal molecular form is, you have to double their atomic mass, of course. Still, 82.03 grams per mole, 0.889 moles in 1 liter. I have 1 liter, 72.9 grams per mole. That's how you work these problems. You'll have, when I make up a test, you'll have these exact same problems. I'll just change the value there and see if you got the concept. I'm not going to work you and make you do too many more. Practice doing these, and I would think by the time of doing 8, you'd be pretty experienced at it. Goodbye now, and see you for the second part of exercise 4.4 in the next video.